To solve limits algebraically, we won't require the use of a graph or a chart to help visualize what is happening to the function. Instead, we'll find that we can often just use simple algebra to calculate limits. So to help explain this, I'll draw some arbitrary function. So maybe something like that. And let's say this is C and this is L, and this coordinate right here is just CL. So we can say that the limit as x approaches C for this function f of x equals L. And for this particular function, we can also say that f of C equals L. And we know that these two are actually not saying the same thing, right? It's just in this particular case, they happen to have the same output, which is L. But actually, it turns out that for many, many cases, this is true, where you have an input and an output, and then the limit as x approaches that input does equal to the same output. So we can use this to our advantage and create a strategy called direct substitution. So this is the most common strategy when it comes to solving limits. The reason is because this is almost always, or in many, many cases, applicable to a function. For many functions, you can use this strategy. And it is way faster than drawing a graph or plugging in values into a chart to see what the values approach. So direct substitution relies completely on basic algebra. And what it is basically saying, I'm assuming this is true. For some function, this is true and this is true. So what I'm going to do is, instead of doing all this, I'm just going to plug in C into this function and I'm going to get L. I'm just going to do this operation, which we all know is usually just basic algebra, and I'm going to get some number L, and then that's going to be the answer, because these two obviously give the same outputs, right? So I'm going to better illustrate this using some examples. So example 1 says, the limit as x approaches 2 for 3x squared minus 5x plus 9 equals some number, and we want to find that number. So we're going to use direct substitution here. So the first step in direct substitution is we're going to assume that we can simply, let's say this is f of x right here, okay? F of x. We're going to assume that we can simply just plug in 2 into this f of x, and the number we get is the number right here. So you can see here that this is just algebra, right? We just plug in 2 into this this equation right here. So 2 squared times 2 squared minus 5 times 2 plus 9, right? 3 times 2 is just 12, minus 5 times 2 is 10, plus 9. 12 minus 10 is 2, plus 9 is 11. So f of 2 equals 11. But because in many, many, many cases, the input of some value into a function and the resulting output has the same pattern in when you use the limit where x approaches that input. So in this case, 2. So we can just say this is 11. So example 2 says, the limit as x approaches 1 for 5x cubed minus 6x squared plus 2x minus 1 equals something. So once again, this is f of x, okay? This right here, that's f of x. And what we're saying is that using direct substitution, this is equal to f of 1. right? So all we do is we just plug in 1 here. So this would just be 5 times 1 cubed minus 6 times 1 squared plus 2 times 1 minus 1. 5 times 1 cubed is just 5, minus 6 times 1 squared is 6, plus 2 times 1 is 2, minus 1. 5 minus 6 is negative 1, plus 2 is 1, minus 1 is 0. So right here, this is, once again, the idea of direct substitution. We're just inputting this value that x approaches into this function, and we get 0. So another example, example 3. The limit as x approaches 5 for the square root of 4x minus 11. So this is f of x once again. So we're saying that due to the strategy of direct substitution, this is just equal to f of 5. So we just plug in 5 right here. So we have 4 times 5 minus 11 and the square root of that. So 20 minus 11 is 9. And the square root of 9 is 3. So this is very simple here. And you can see that direct substitution makes things much faster rather than having a calculator and plotting in values to make a table and seeing what y approaches, or drawing a graph, right, and trying to observe what's happening. This is all just basic algebra that can be done in very few steps. Okay, example 4. The limit as x approaches negative 3 for 2x squared minus 17 over 2x plus 8. So once again, the same idea. By now we know we should just input this x value into this function, and it should be the same number as what this total equation means. So 2 times 3 squared minus 17, 2 times negative 3 plus 8. Negative, but it doesn't really matter in this case, but just to be clear. Okay, so negative 3 times negative 3 is 9. 2 times 9 is 18. And 18 minus 17 is just 1, right? 2 times negative 3 is negative 6. And negative 6 plus 8 is 2. So by now, you can see that this process is very easy, especially if the functions themselves are easy. So for this case, it's slightly different. You have a trig function, but it's still the exact same process, right? You're assuming this is a function, and you input this value into the function. So 3 sine 3 pi over 2, right? I just plugged in this pi over 2 into the x. And what is this? So if you don't know this off the top of your head, you can just draw a quick little unit circle. Okay, 3 pi over 2. So what is that? That's the equivalent of saying 3 divided by 2 times pi. And 3 divided by 2 is just 1.5. So 1 and then 0.5 pi. So like that. And we know that at this point, sine is negative 1, right? So it's just 3 times negative 1. So the answer would be negative 3 here. Okay, one last example. It's still the exact same strategy. You're plugging in this x equals 2. So 7e to the 5 times 2 minus 10. So 5 times 2 is 10. 10 minus 10 is 0. So 7e to the 0, right? E to the 0 is 1 because anything to the 0 is 1. So 7 times 1, which is 7. And our answer is 7. Alright, so now after several examples, you can tell that direct substitution happens, or is maybe it's applicable in a variety of situations. So we can actually write this sort of general formula which says that the limit as x approaches c for f of x equals f of c. But this is not always true, okay? This is basically saying if direct substitution is applicable, then do this right here, where you input your value c into this function, and that's equal to this. However, this may not always work, right? For example, maybe you have a function like this, and that's c, right? And that's L, or maybe whatever value. Functions with points where they're open dots, right? They're undefined. This obviously won't work in this scenario, or maybe asymptotes, which is basically just saying that this function it approaches this imaginary line, but it never really reaches it, right? Or there's even something called oscillating functions. So they're like this at first, and then they get very, very, very close together. So it's this would be C, and you wouldn't there wouldn't be an input value. This would be undefined as well. So you can see like there are plenty of cases where this is not true, where you can't use this, where you can't use direct substitution. But direct substitution, more often than not, is the #1 method when solving any kind of limit. Okay, you should always try direct substitution first. If it doesn't work, then resort to other methods, which some of them I will explain in future videos.